Hey everyone, welcome back. So this is a continuation on our discussion about recursion, and specifically today we're going to be taking a look at what recursive backtracking is. So you can think about recursive backtracking as being a way to check different parameters and then or different situations and then evaluate whether or not we're going to recurse or not. Um, and it's so here's an analogy. So if you're looking at this over here, this is a maze, right? So what we can do is we can let's start at our initial condition. So we're going to be at some point, let's say over here where my mouse is. Ignore the yellow dot for now. But yeah, so my mouse is here, right? And then I want to check the next position. So I can either move down or I can move sideways, right? So if I move, you see my mouse, if I move down, right, my mouse, I'm going to check that point. And then if it's a viable path, then I will continue moving down. If it's not a viable path, then I'm going to backtrack. I'm going to go from down here up to here again, and then I'm going to check another position. I'm going to check the horizontal. My horizontal is valid. Then I'm going to recurse there, change my position, and then again check down, and so on and so forth. So let's kind of break this down into some pseudocode so it makes more sense. So again, as in any recursive function, we have to have a base case over here, and we have to have the recursive methods, which we're going to have over here. So basically, the base case is if we've reached the final destination, return and print the solution matrix with our path, right? Basically means if we've reached our target, we can stop because that's it. Like we've reached our goal. That's the base case. Now, if we haven't reached the base case yet, right? Then what we need to do is we need to kind of mark the current index of our matrix as being 1. What that means is that we're going to initialize our solution matrix as just being 0, all 0, meaning that everything we're going to say is not part of our path, or is part of our path. And then we're going to mark the current, is not part of our path. Then we're going to mark 1 as being part of our path, right? And then from there, we go on to step 2, which is we check in the horizontal direction to the right of our current index, right? Because we're assuming, like, let's say this is our maze, right? This is our starting point. The end point is always going to be the lower right-hand corner part. So we're going to move to the right first, and then, the zeros represent walls, right? And 1s represent part of our path. So if we move to the right and then we see, we've hit a wall, that means that we can't move in that direction. So then we check, the horizontal move doesn't lead to a solution. Then try moving down. So we then will move down from our initial point. And then, look, 1 is viable because 1 is part of our path. 1s represent clear paths. So if that's the case, then we recurse. So we repeat the same thing on 1. So again, on 1, we check the horizontal. Look, it's a viable path. We recurse. So again, we change position, so now we're here. Now again, we move horizontally. We're at 0. We can't do that. We then go here. We recurse, so on and so forth. Now, let's say I have a point where neither the horizontal nor the vertical moves lead to a solution, right? Then we know that that index is not part of the solution path. We then mark that index as being 0. This means it's not part of the solution path, meaning this is the point where we backtrack, meaning we kind of reset whatever changes we had made, restart, and then try different things. So over here, let's look at a point that we could probably backtrack from. Let's say we're at this point. Well, let's see. well, here, and then we can go horizontally. So, oh, this is part of the path. This is 0, however, right? We go down. Oh, it's blocked. Like this is clear, but this is blocked. We can't check horizontally because that's not satisfied. We're at the edge. We go down, it's blocked. Then we go back and we actually mark this 1 as being 0, which makes sense, right? It's not going to be part of our path because our path, if you look at it, it's going to look something like the sequence that I'm highlighting with my mouse. So that's why we can mark this as being 0. That makes sense? All right. So that's kind of our pseudocode. And then now let's kind of like do some helper functions first. We can have a helper function to print the matrix. This is a very simple printing function, right? It's a nested for loop. Then we also, this part is important. We need to check that the point that we're at is part of the index, is part of our matrix. Because if not, if we don't check, then we're going to have index out of bounds errors, right? So we need to make sure if big N is the number of cells, of rows and columns. Again, we're working with squares, so N represents both the columns and rows. If X is in between 0 and N, and Y is in between 0 and N, and it's clear, right? If the maze, if that point is clear, then it's a valid index, right? If none of these are satisfied, because these are all AND statements, then we return false. It's not a valid point, we can move on. This is our main, so what you'll see a lot of the times in recursive problems is that you're going to have helper functions and you're going to have like the parent functions. So helper functions are just a way to actually embed the recursive methods in, because the thing is like the main method, it's going to be printing like a lot of things. It's going to be initializing the solution matrix. If we were to have our recursive call on maze solver, then we'd be always initializing the solution to be 0, and we just have an infinite loop, right? Or an infinite recursive method, and that would be a problem. So instead what we do is we kind of break our problem down and we have a helper function. The helper is that where we actually do the recursion, right? So here you can see that we have this, and you see we call it twice. We're calling the function twice. Why? Because in the first point where we, well, let's actually, well, I'm going to go over why we call it first, but before that, we're going to just see what we do starting from the top. So again, look at the parameters. We take in the maze matrix. X and Y is the index that we're checking. The solution matrix is the solution matrix that we also take. So this is what we're going to be changing. N is the size of our matrix, being the number of rows and columns. So again, here, the base case is that we've reached the destination, and that is that our X is at the lower, at the rightmost position, and Y is at the lowermost position, right? That we talked about our maze as having the solution at the lower right-hand corner. So if that's the case, we return true. We've solved the maze. If not, then we have to do deeper and then do the recursive calls. So first we check if it's a valid index, right? We have to check if it's valid. If it's not, then we don't check that point. So then we have to gamble that the current index is part of the solution. So in our solution set, we're going to say at the position that we're at, we're going to set it equal to 1, right? We're gambling. We're saying, oh, I'm speculating that it's 1. I want to see what happens if I set this to 1. Then here, this is what we call the recursive function, and over here you see that we're going to check the horizontal direction, meaning we're going to change X by 1 and we're going to check. So we're going to call this, what it does is that it jumps back up, right? And then it says, okay, check the base case. If we're not the base case, again, then gamble that the current point that we're at X plus 1. So if we were originally at 0, we increment X by 1. Now we're at X equals 1, right? Then we're going to gamble that X is 1, right? We're going to keep on doing this until, like, it only works if it's a valid index, right? So if we bump into an X that is actually 0, right, then that means we're not at a valid index, and that means that we are done with this part of the recursive call. We then have to check the up and down directions, or down directions specifically. So here we're gonna again increment Y, right? And in this case, we're gonna do the same thing. We're gonna jump up here, and we're going to check if the Y is a valid index, sorry, no, this is the base. Here, we're going to check if by changing y we're at a valid index. If that's true, then we gamble that our solution matrix also has at that y position and the x position, which we haven't changed, that's part of our solution. So we set it equal to 1, and then we keep on doing this, right? So and then if both these don't return true, right? If none of these are satisfied, then we backtrack and we say our original position, we're going to set it equal to 0, or the current position that we're at, we're going to set equal to 0, right? So this is our helper, and then over here in our main solver, we're going to call the helper. And then if it returns false, meaning that if we exhaust all options and it returns false, that means that we don't have a solution, and then we return false. If, however, it's not, if it does have a solution, if this is true, right, then we print the solution matrix and return true. So let's see this over here. So we're going to have n equals 4 because the number of rows and columns is 4. We're going to initialize some sort of maze, right? And then we're just going to call maze solver, maze n. And the output that we get is this. And again, in this function, there are multiple solutions. Each time that you run it, you might get a different answer. And this depends on the initial maze condition, right? Cool. So I think that's it for recursive backtracking. Hopefully you've enjoyed this lesson. And I think next we're going to cover object-oriented programming, which should be fun. But yeah, again, leave any comments or questions in the comment box below. Please like and subscribe. Thank you so much. See you next time.